Robotics. My name is Dr. Michelle Johnson, and I have the distinct privilege of introducing my colleague, Dr. Hao Su. Let me just share a few detailed information about Dr. Su. Dr. Su will be presenting Unleash the Tether High Force Actuators for Portable and Efficient Soft Robots. Dr. Su is an Irwin Zan endowed assistant professor in the Department of Mechanical Engineering and director of the Lab of Biomechatronics and Intelligent Robotics at the City University of New York. He was a postdoctoral fellow at Harvard University and the Weiss Institute for Biologically Inspired Engineering. Prior to this role, he was a research scientist at Philips Research North America, where he designed robots for lung surgery. He's a junior chair of the IEEE RAS Technical Committee on Mechanism and Design. He received a prestigious and National Science Foundation Career Award, the Toyota Mobility Challenge Discover Award.
Which one?
And an additional variety of different additional awards. He is currently directing Center of Assistive and Personal Robotics for Independent.
You have.
Can anyone who has not muted their mic, please mute their mic so that you're only hearing my voice? I appreciate it. So he is, he's currently directing the Center for Assistive and Personal Robotics for Independent Living, April, which is funded by the National Science Foundation and the Department of Health and Human Services. Without further ado, I want to bring you Dr. Su.
Thank you, Dr. Johnson, for the kind of introduction. Yeah, can I share my screen? Yeah, thank you. Yeah.
You had already, it was already shared, so you just unshared it. Okay, there you go.
Can you see my screen?
Yes, we can.
Okay, yeah, let me 1 second to. Hey, good morning, good afternoon. It's a great pleasure to be here today. Thank you for having me. I still remember the days in 2018 when I visited Livorno for the first RobotSoft conference. I hope to meet everyone in person in the near future. Today, I would like to share with you our research that is under the intersection of robotics and medicine. Our lab focuses on design and control of high-performance robots with application in rehabilitation and surgery. This is a truly fascinating and emerging field that involves many fundamental research and exciting applications to solve real-world problems. In the last decade, we have made significant progress in information technology. Smartphone is ubiquitous, which is the interface between cyber world and the human. But there's a limited system that can deliver physical service. I envision robots will be the new interface between human and the physical world to augment people for various tasks, from elderly care, manufacturing, to construction, disaster response, and many others. State-of-the-art robotic systems are primarily rigid and operate on position control. They are highly precise, but terrible for physical interaction. Our research aims to design and control soft robots for physical collaboration with humans in ubiquitous settings. The question we are looking for answers is what kind of design and control solutions can enable this paradigm shift? In particular, we are very interested in the fundamental limitations of robots, in particular soft robots, and how we can translate these technical innovations to address the unmet needs of biomedical applications. Our multidisciplinary team is composed of talents from 4 research areas, including mechanical engineering, like Antonio, he's from University of Pisa, like electrical engineering, control, and biomechanics. Our clinical collaborators are also leading experts in biomedical science. I also established the Center of Assistive and Personal Robotics, the APRO Center, that is composed of 9 faculty from New York University, Rutgers University, and the University of Texas Medical Center. In my lab, we focus on 2 domains. On the left, one domain is robotics, where we study design and control. Our approach is unique as we create component technologies like sensors and actuators. We also design robots from scratch, and then we develop controllers to embody intelligent robots. On the right, the other domain is scientific discovery. We use robots as a tool to address unmet needs in medicine, both in surgery and rehabilitation. We want to leverage robots to understand medicine and biology. In my lab, we have developed multiple like high-performance robot platforms in the continuum care, ranging from like soft exosuits for musculoskeletal injury prevention to MRI-compatible minimally invasive surgical robots for cancer diagnosis and neurosurgical procedures. Those are essentially continuum concentric tube robots. In the last 4 years, we have been focusing on wearable robots for home-based rehabilitation with application in pediatric rehabilitation and also for musculoskeletal disorders like knee osteoarthritis. Specifically, we have developed several key enabling technologies, including really lightweight motors and high-speed soft actuators and high-force soft actuators. Leveraging those components, we have designed, we think is the most lightweight powered exoskeleton, also with controllers to assist real-world locomotion. We believe that those innovations will enable a paradigm shift of assistive robots from clinic-based to home-based rehabilitation tools. We have shown that our lightweight robot is able to significantly reduce energetics during human walking. In addition, we have some promising results to demonstrate that robots could be medicine, for example, to reduce pain of people with knee osteoarthritis and also improve mobility for children with cerebral palsy. Generally, if we observe robots through the lens of design and control, in terms of compliance and the lightweight, the design approach of many state-of-the-art exoskeletons has no difference with industrial robots that are heavy, rigid, non-compliant, and even dangerous. In terms of intelligence, researchers developed wearable robots that can assist human running, and in addition to walking assistance. But many systems are still tethered and cannot be used for community settings. In my lab, we aim to develop a really lightweight powered exoskeleton to minimize the mass penalty of wearable robots. We seek new design solutions to make a robot really lightweight and compliant. And the design objective is to reduce metabolics. Of course, for wearable robots, there are many other metrics in addition to metabolics, like muscle activities, but metabolics is certainly one key metric in this community. If you look at the other dimension in terms of control, we want to develop controllers that can assist versatile activities. It's not only for walking, as many state-of-the-art robots focus on, but also for many other irregular gaits or irregular activities. In today's talk, I will cover 3 topics. The first one is a compliant robot, in particular, this untethered compliant wearable robot. Then I will present soft material wearable robots. For the third topic, I will share with you our control research, namely versatile controller for multimodal locomotion assistance. Let's start from the first topic about compliant wearable robots and why we want to work on these high torque motors and high torque exoskeletons. Our robot development process always starts from understanding the unmet needs in medicine. In this case, it's biomechanics. Human locomotion is actually a complicated process that involves coordination of multiple limbs. A unique feature, as you can see from this diagram, the x-axis is a gait cycle from 0% to 100% of single stride. The vertical axis is the ankle joint moment. And you can see a unique feature is that human walking requires high torque. Ankle joint generates about 120 Newton meter torque in about 200 to 300 milliseconds. Even if we provide partial assistance, let's say 30% assistance, actuator is required to generate about 40 Newton meter torque. Right? If we look at this, the bottom red diagram, this is the torque speed profile of a human ankle joint, and the exoskeleton that provides partial assistance is located here, right? However, conventional actuator typically can only produce about 0.5 Newton meter. So you can see the large discrepancy between the requirement and the motor performance. This is more than 100 times of capability of conventional motor for wearable robot applications. So how can we tackle this problem? We follow a very kind of like an interesting thinking philosophy. It's called a first principle based thinking. Essentially, it's a physics way of looking at the world. You boil things down to the most fundamental truths that we can tackle these fundamental limitations and to tackle the overall problem. For example, before we started the robot development, I asked ourselves, what are the first principles that limit the performance of wearable robots? If you look at the anatomy of a powered exoskeleton, it's composed of motor, gear, typically high ratio gears, and variable structure. And those high ratio gears, typically around the 200 to 1, 300 to 1 gear ratio, results in high friction and high inertia of the robot. Thus, most wearable robots are actually resistive to natural movement, in particular when it's unpowered. Our exoskeleton aims to make the robot not only lightweight, but also compliant and truly assistive to human movement. We have some like a holistic solution from high torque motor to low ratio gear and some different transmission mechanism from rigid transmission to soft transmission. Similar to the revolution in automotive industry, my lab have been working on actuator electrification research for robots. If you look at the 3 metrics to quantify collaborative robots, including compliance, bandwidth, and efficiency, conventional actuators have high bandwidth, but very rigid and suffer from low efficiency and low compliance. Series elastic actuator is still kind of like a state-of-the-art solution, can improve compliance, but by the addition of mechanical spring between transmission and the load, right? But it has a mediocre bandwidth and efficiency. Quasi-direct drive essentially is we leverage some like a high torque density motor with low ratio transmission mechanism. We'll be able to have high compliance, high bandwidth, and high efficiency. So it can optimize all 3 metrics for collaborative robots. But the key enabling technology here is the high torque density motor. For example, our electric motor is able to provide more than 9 times torque than conventional motor. And basically about 11% of mass of conventional motor made by Maxon. As shown in the bottom left figure, our motor is more similar to human motion characteristics, higher torque and lower speed. And it generates large torque and relatively lower speed. Our motor, if you look at the diagram on the right, it not only has better performance with kind of like conventional Maxon motors, but also have higher torque density than some of those drones motors. For example, this T motor has been used widely for some like the robots by MIT and many other groups. To achieve those performance, we developed 2 physics-informed design methods. The first method is motor topology optimization. Instead of conventional motor that is based on interior rotor design, we create an exterior rotor topology, shown as this kind of like a colored circle. If you look at the diagram on the bottom right, and this exterior rotor topology can produce a higher torque density than interior rotor design. The second method we developed is the mechanical and the material optimization. We are able to reduce the rotor inertia by 60%. In addition, we also figured out some high temperature wear coating methods, so motor can operate at the nominal torque while the highest temperature is still fairly low. In addition to the first principle based motor design, we also leverage mechanical design to develop a lightweight robot. Our robot is lightweight is not only because the high torque density motor, which is essentially lightweight motor, but also based on the simple mechanical design. If you recall the slides about SEA series electric actuator, actually to add the spring, it requires a very complicated mechanical structure. So the overall system is actually complicated and also in general is kind of like heavy and bulky. So for example, for our, this is the hip exoskeleton here. And as a reference, motor design and the robot design, those two combined together, we resulted in really much higher torque density than state-of-the-art exoskeletons. For example, if you look at the last 2 rows in terms of torque density, and we have a much better performance than one of the best powered hip exoskeletons. And based on biomechanics simulation, we expect this robot to significantly reduce metabolics about 25%. In addition to this portable robot, we also studied design some tethered robot to further minimize the variable mass, right? We can isolate the actuator from the person, so the person only need to bear the mass of the variable structure. Because if the robot is too heavy, it significantly increases the metabolics penalty to the person. This is a robot from Humotech. It's a tethered system. It's a spin-off company from Carnegie Mellon University. And you can see here, they are based on the AC motor and the variable robot. The variable structure is actually kind of like a heavy for about 7 kilograms for one hip exoskeleton. And they can generate a really significant amount of torque to a person. In our design approach, we want to use a DC motor because it's much smaller and much more affordable. And the variable structure we designed is also pretty lightweight, about 1.5 kilograms. And though we can, our torque is slightly less, but it can already generate more than 80% of torque for most drones. And one key feature is that we can, this robot still allows natural range of motion, because many exoskeleton, for example, some tethered exoskeleton doesn't really allow the natural range of motion for movements like squatting or stair climbing. In addition to this compliant robots, and you can see it's a structure-based soft robot, right? And we also work on soft material robots through soft actuator design to achieve high force, and also we developed the soft exosuits with high force and tethered in a tethered manner. The previous robots I just presented are compliant, but their materials is not soft. It still has rigid joints that cause misalignment issue between human and a robot, as shown here, right? So joint misalignment is a key limitation of rigid wearable robots. Soft material robots that use soft materials like rubber and fabric is very suitable for wearable applications because there's no joint for those robots. So there's no joint misalignment issue as a rigid robot. But the fluid-driven soft robots typically have low forces, and it requires a heavy tethered pump to generate the fluid. Actually, from a mechanical design perspective, if we think about the energy transmission from a tethered pump to some like a pneumatics mechanism, I consider pneumatics is a transmission, and this pump is actually a very important component of the actuator because it converts electrical energy to mechanical energy, right? So this pump is actually a very important component of actuator. From this perspective, we consider that motor and pump limitations, not only the pneumatics or hydraulics structure itself. Because many fluid-driven soft robots are tethered, to unleash the tether, the key objective is to design high torque density and high efficiency robot components. Our method is the actuator electrification for soft robots. In this case, soft material robots. Here we use several metrics, including the overall weight, efficiency, and the force. This tether system can certainly produce some high force, but you can see it's certainly too heavy as a portable system, and the overall efficiency is pretty mediocre. When we started this, our design process, it really puzzled me if it's possible to generate human scale forces in a portable manner, right? For example, for wearable robots, if you think about the exoskeleton, it requires around at least 300 Newton to 500 Newton force. That's really a significant amount of energy from this actuator. In the last 3 years, we figured out some electro-hydraulic solution that we need to design custom. We need to design and customize a lot of mechatronic components, including motors, magnetic pumps, and electronics, to enable this electro-hydraulic actuator solution. To convert motor motion to fluid actuation, pump is very important. To improve the system efficiency, we developed some custom pumps. And you can see from the left figure, conventional pumps have very low efficiency, about 15% mechanical efficiency, resulting in less than 10% overall system efficiency. For portable robot application, we design and customize some very cool component, this pump. We call this magnetic pump. Is much more compact and efficient than those bulky solutions. It can dramatically increase the overall system efficiency in concert with our high torque density motors. In addition to, I talked about the motor solution for soft robot and also some one magnetic pump solution for soft robot. We actually also work on some transmission solutions. For example, in this case is a pneumatic transmission. We developed some bistable mechanism-based soft actuator to achieve high speed. I think this is one of the one of the first instability-based high-performance soft robot. And you can see from the bottom figure here, the robot has two stable states and one unstable state. It leverages this nonlinear phenomena to rapidly switch between two states. The robot is able to amplify the actuation speed by 20 times than conventional actuator, and it produces kind of like a high-speed, kind of like a running or crawling soft robot. The same principle can also be used to design high-speed underwater robots. It's very interesting to use one principle to guide the design methods for different applications for both overground and also underwater locomotion. In addition to locomotion robots, instability was also used for soft gripper design. A unique feature of this like a instability-based soft gripper is we can modulate the stiffness by spring pretension. If you look at the bottom figure here, we can dynamically change the spring pretension to regulate the energy, and also to ultimately to regulate the force output of this robot. And the stiffness can be modulated to high stiffness to grasp heavy objects, or some low stiffness to handle some fragile objects. It's very suitable for manufacturing and assembly applications. Many soft robots are based on pneumatics, and we also think hydraulics is a promising alternative for higher force density. Using this magnetic pump shown here, the mass of our actuator, this hydraulic actuator, is only about 300 grams, but it can generate about 500 Newton force with a relatively kind of like a low pressure level. Our electrohydraulic soft actuator is able to generate human scale force while being untethered and lightweight. And you can see from this video, and the system is pretty mechanically very resilient to impacts. You might ask me why we make so many components and actuators. You can see how useful when we use those components to design exosuits. For example, we are very excited to find that the performance of our electrofluid exosuit overall has only about 2.6 unilateral mass. The bilateral mass is about 3.8 kilograms, and including all components, motor, pump, battery, and variable structure. And it can be worn under garment, and it's also a modular solution that can be designed for hip, knee, and ankle assistance. I talked about two design solutions for compliant robots and also soft material robots. Design is certainly one key aspect of wearable robots. Control is certainly very critical for the performance of wearable robots. I will share with you about our some like modeling work and also some control work to enable this versatile control of different kinds of like wearable robots. Why? Oh, any? Okay. Is there some question? I see someone. Can you please unmute yourself if you want to ask a question?
I have a question. Can I?
Yes, please. Yeah.
So you say that 500 Newton is required in the couple of slides before. I didn't understand if, let's say, how it was calculated or how it is a target. Second one is in the pneumatic actuation, you showed the air pump, but maybe I missed that point. You're eliminating the air pump source and then you're using the magnetic pump for the pneumatics systems, or if I understood wrong?
Yeah. I think, yeah, good, those are really good, two good questions. I think the fourth requirement, right? So if you look at the, let's think about the fourth requirement or top requirement, right?
Yes.
And for the lower limb, right? So if you think about the lower limb, there are 3 joints: hip,
Yes.
hip joint, knee joint, and ankle. And overall, the ankle joint has the highest top requirement, about at least 100 Newton meter. So if you think about we provide a partial assistance, because if you want to provide a full like a 100% assistance, that's a little bit kind of like for people who are fully paralyzed, right? And in our case, we want to provide a partial assistance that can really, because of many people, like for people with stroke or knee musculoskeletal disorders, they only require partial assistance, right? So the 100% assistance is too heavy, right? So if you calculate the torque, right? Let's say 100 Newton meter multiplied by 30%, it's at least 30 Newton meter, right? But this is kind of like a range in terms of some people want to assist 50%, right? And depend on different joints and a different percentage. But if you see, let's say the ankle 30 Newton meter, and we divide it by the moment arm, right? And actually, if you think about the ankle exoskeleton from, for example, from several universities, it generates using the cable solution is a 700 Newton, 700 Newton, right? So actually, if you want to provide a little bit of lower level assistance, I think it's around at least 300. For example, I worked on the cable driven ankle exoskeleton. 700 Newton is really, really required. For the hip joint is 300 Newton, right? So the 500 Newton is roughly a ballpark. So I would say from 300 Newton to 700 Newton, basically kind of like a high force. Yeah.
So 30% basically you.
Yeah, 30%. So that's no kind of consensus, right? It's kind of like a trade-off, right? 30%, yes. Maybe you can, yeah. I think from 30 to 50% is kind of like a good percentage, right? And when you ask the second question, is basically we want to. That's also really a good question. So we want to different from the kind of like the first solution based on kind of like a tethered pump. We want to get rid of this big pump, and we don't really operate on. We don't connect to the tether to a wall, right? So we use it's battery operated, and also based on this motor and a magnetic pump system. So this is a kind of the system structure. So roughly you can see from this diagram, this picture, and yeah, so it's kind of like a compact solution, right? Yeah.
Yes, and also you use it for the hydraulic actuation, because in hydraulic also usually researchers don't prefer, because hydraulic usually creates problem. Let's say conventional hydraulic systems, that the forces are high and the maintenance and those stuffs.
Right.
From literature surveys, so you also solve this problem, I think.
Certainly. I think hydraulics. I think pneumatics, hydraulics, they have both have pros and cons, right? And I think the unique opportunity for general fluid-driven robot for variable application is here, because if we think about high force, right? Actually, it's not very difficult to design some high force actuator, right? Like this from the Professor Suzumuri's lab. It's really a nice, very cool hydraulic actuator, right? But for this portable application, this presents some unique challenge, but also unique opportunity, right? And I think in this space, right, it has a high force, but also to make that portable, it's really something pretty unique, right? Because, for example, this one is also a famous robot from University of Colorado, right? But generally, it's a little bit kind of like a low force end, right? It's not really designed for variable application. For this grasping, this kind of actuator is good. But for exoskeleton, this is really a big challenge. Even for us, I think it's still not really, it's very, very difficult to design high force and a portable actuator. And also, I agree with you. There's some leakage problem, right? For pneumatics, leakage is not a really big deal, maybe, right? But for hydraulics, it's really not as clean as pneumatic, right? So there's certainly some drawbacks of this kind of like a solution. Yeah.
Yes.
So I'm gonna thank you, Dr. Su. I'm gonna ask Could I ask everyone else to hold their questions until the end? Just ask Dr. Su to go ahead and finish his talk, and then
Okay.
if you really need to write it down, put it in the chat, and then we'll try to field questions at the end. Thank you.
Cool. Thank you. Yeah. So let's go back to the control challenges. Why control is important for rehabilitation. In terms of the principle of neural rehabilitation, devices should maximize human effort and engagement of user. Right. My clinical collaborator at National Institute of Health, she has been keep telling me to develop some controllers to increase locomotion activity of children with the cerebral palsy. So we really want to get away from this design and control paradigm to some really versatile controller. Our design objective for the controller is to develop some synchronize assistive talk with human for multiple activities. Right. For a single joint, we want to come up with some talk assistant profile that can really synchronize with the human activities. To this end, we have two tasks. The first is to model the human-robot interaction and to understand the robot impact on human. The second is figure out this talk profile. We developed a unified model that can capture the dynamics of motor, transmission, and variable structure. From this dynamic model, we are able to understand the property of different actuation paradigms. And we developed, from this modeling and experiments, we found that our actuator has both high compliance and high bandwidth. In this case, I'm talking about the compliant actuation, the quasi-direct drive actuation, to achieve high bandwidth and high compliance. From both simulation and the experiment, we found that the quasi-direct drive actuator is able to overcome the limitation of conventional actuator and the series electric actuator. In this case, the QDD actuator demonstrated with the high compliance. And we actually also designed, using the QDD actuator, we designed a cable-driven, kind of like a soft robot actuation. And it also has a high compliance with this cable actuation. In terms of the bandwidth, we found that the series electric actuator has to compromise the bandwidth to ensure compliance because of the spring mechanism. While quasi-direct drive is also superior in terms of bandwidth. So high bandwidth makes wearable robots more responsive and being capable to handle unexpected events, right? So this quasi-direct drive actuation really can ensure both high bandwidth and high compliance. For our cable-driven quasi-direct drive actuator, it achieved really good tracking accuracy. And we also shown that we can reduce about 75% of muscle activities during a squatting activity movement. When we think about how to use those robots, many wearable robots are designed for neurological disorders like a spinal cord injury and a stroke. Because those individuals generally have more severe gait impairments and more willing to tolerate the mass penalty of wearable robots. We have been working on different application, like a musculoskeletal disorder, like a knee osteoarthritis. The idea is to reduce the loading to relieve pain for people with a knee osteoarthritis. We have obtained some very promising results to reduce about 80% of pain in 6 subjects. Their pain scale have been reduced from 9 to 1 to 2. So the smaller the better. We also shown that we can also reduce the muscle activities of people during walking. Our team also won this Toyota Mobility Discovery Award using this cable-driven soft robot.
Put this on, it actually helped me. I felt that I had more stability, it helped my balance, and my gait kind of went very natural. I felt very comfortable in the sense of, wow, this is going to be my friend.
I love it. It took about, a minute because it's pretty easy. I'm walking a lot lighter. It's very low profile. I don't hear noise when I'm walking. Everyday use, this is perfect.
They have to tell us what they need. They have to tell us what they want, so that when we finalize the soft exoskeleton, it is something that will be useful, meaningful, something that will help them in their recovery and their activities of daily living.
Another aspect of controller design is to develop some like a continuous control methods. And this continuous controller is important for wearable robot control, because if you look at this one state-of-the-art controller, it uses predefined piecewise torque profile. The x-axis is a joint angle. The y-axis is torque. The torque profile is not smooth and susceptible to varying gates. And also there's no one-to-one mapping between joint kinematics and joint torque. So it has to rely on discrete gate detection, like finite state machine methods and discrete torque control. Our method is based on continuous detection of gate that produce more robust and smoother assistive torque profile. In addition, it is able to produce one-to-one mapping between kinematics and estimated joint torque. For a data set of 23 people, we figured out how to handle those massive data, as biomechanics produce a lot of data, including walking at different speeds, gait cycle, and many kinematic data, including joint angle, angular velocity, and joint torques. To estimate the joint torque for real-time synchronized control, the robot torque, we want the robot torque to synchronize with the biological torque. We look at the gait biomechanics, and it turned out that walking is still complicated process, and we can separate it into 4 phases, including double support and single support. And after the push-off phase, the gait biomechanics goes into double support again, and finally limb will be in swing phase. We observed that there are 2 dominant stiffness modes during gait cycle. This inspired us to separate the gait cycle into 2 phases. The one is a high stiffness phase, contributes to this kind of like a biological torque, and low stiffness phase. We performed a lot of like exploratory data analysis, so we can separate the gait phases from using the kinematic data. So basically, we are trying to map the input from the sensor to the torque estimation. One solution we tried is map the joint angular velocity to estimated torque, and then you can see it's just no one-to-one mapping. We also tried like a angular. This in this case is a knee joint angle difference, and although it's able to separate these 2 phases, there's still no one-to-one correspondence. The third option is we extend this to 3D. We used the angle, joint angle, and angle difference to estimate the biological torque. It can match the data fairly well, but we found that there's still a kind of like the discrete gap between those 2 phases. To overcome this discrete limitation, we came up with some very simple solution. We use some smooth fraction called, for example, in this case, sigmoid fraction, readily used in neural networks research, to linearly combine the 2 stiffness modes. The blue one is stance phase data, and the red one is the swing phase data. We can end up those 2 modes by the contribution of high stiffness torque and low stiffness torque. By putting them, adding them 2 together, we can generate estimated torque. So this is actually a very simple way to use sensor data to estimate a joint torque. but it's not very trivial to figure out the stance phase and the swing phase using our variable initial measurement unit sensors, MU sensors. So we figure out some like a nonlinear optimization method to identify the optimal hyperplane to separate those two different states. We obtained some really promising results. For example, if you look under the in the time domain, in terms of gait cycle, the estimated torque can match the biological torque very well for all 23 subjects. And also, if you look at the stiffness plot, right here, you can see this controller can match the high stiffness and low stiffness profile fairly well. And also, this kind of like estimation and the gait synchronization method can work well for low speed, high speed, and self-selected kind of like a medium level speed. So it's really practical and a simple solution that can estimate the joint torque continuously and for many locomotion activities from like a forward walking, a stop, and backward walking. We further developed a robust torque estimation controller for multimodal locomotion. Versatile control for multiple activities is considered a grand challenge in wearable robot, and most research is primarily focusing on walking assistance. Our controller can smoothly assist loaded walking, jumping, and squatting without using activity classification. These are discrete solutions. More importantly, we have obtained some really promising results that our lightweight, in this case, knee exoskeleton, one single knee exoskeleton can assist loaded walking, and it can also augment human performance to help people to jump 12% higher, and also can increase 50% maximum number of squatting for able-bodied population. As a summary, our research investigates the fundamental limitations of soft robots to tackle biomedical challenges. We believe that soft wearable robots can be designed as untethered with high force. In terms of the engineering impact, we think this physics-informed design can create lightweight and some new actuation paradigms. And also in terms of impact on scientific discovery, we developed some like optimization-based controller to provide a versatile assistance to understand human-robot interaction. And this powered robotic devices could be useful assistive tools to enable community-based rehabilitation. For example, as a device to reduce pain. So it can be used for neurorehabilitation and orthopedic applications. I think overall, those enabling technologies, including motor and the sensor technology, can also be used for other biomedical applications, including surgery and even regenerative medicine. In terms of our future research, I envision to explore two future projects. The first is a biomechanical study of this assistive robot to create a new research areas. For example, we want to understand the efficacy of these robots for broader population, for people with knee osteoarthritis and also cerebral palsy. And we also think maybe the next big thing in wearable robot is neural robots. And we are working on some like this robotic hip prosthesis. So that's very limited, this hip prosthesis research. Most of the research focus on ankle joint or some focus on knee joint. Here it's a very unique, the hip joint powered robotic prosthesis. And we want to have better understanding about how to restore proprioception, cognitive augmentation for amputee population. Another area I think is physically informed learning with application to wearable robots. In our lab, we also designed this soft back exoskeleton. It's very unique because for back joint, we need to reduce 3 forces. along the muscle and the spine, right? It's very unique. It's one robot. We want to minimize 3 forces. And by leveraging this platform, we are also working on some mechanics-informed neural networks design solutions, like Lagrange neural network based models. In addition to research, I'm also very committed to robotics education. My goal is to develop affordable robot toolkits to lower the barrier to learn robotics. And we have some like open source robot kit, and it can be found from this website, and also has been used for more than 20 student projects at my university. In the end, we truly believe that soft robots could be used for translational medicine to address unmet clinical needs in rehabilitation and also surgery, another research area in my lab, to augment the human, like surgeons, cardiologists, physical therapists, able-bodied individuals, and also people with disabilities. That is the end of my presentation. Thanks for your time. Thank you.
Thank you, Dr. Su. That was an excellent talk. I know there were many questions. Now we can take questions from the floor. If you would just raise your hand, I would try to recognize you. If not, just, we'll try to figure out and get questions answered. If not, if you're shy, put your questions in the Q&A section so that we can also respond. Any questions?
Yes, I have a question.
Go ahead.
I was interested when you speak about the backdrivability of your soft robot. I was wondering, how do you measure the backdrivability? Is there any metrics or?
Yeah. So we use the torque sensor for the we measure the backdrivability for this like a cable-driven knee exoskeleton. There's a torque sensor mounted on the knee joint. So when the person we apply, for example, you can apply use your hand or some other tools to apply some force to the actuator, and we can measure the torque through the torque sensor. Yeah, does this answer your question?
Yes, thank you.
Yeah.
Any other questions? Dr. Su, I'll just kind of, since we're waiting for other people to be brave enough to ask questions, this is a really interesting talk, and I think I'm just excited to see the directions that this can take. Can you talk a little bit about, so the students have a kind of a competition that they're talking about. Can you provide any kind of strategies as the best way of finding or innovating in this particular area? You mentioned you've done a lot of innovation in your space. What would be a good guideline in terms of or suggestions for the students to be able to apply some of the things that you've talked about?
Yeah, thank you for that's a good question. Yeah, thank you for asking that. Yeah, I think what some tentative idea is could be when you think about some wearable or soft robot application, maybe you think about what joint you want to assist, right? There are many joints that could be helpful. For the lower limb, in our case, we actually primarily focus on the knee joint and the hip joint, because that's the kind of like unique joint that, for example, the early exoskeleton research primarily focused on the ankle joint because it generates high power. But if you think about the hip joint, it doesn't have this like a kind of like a spike profile of the power, but the hip joint also generates a lot of kind of like overall energy, right? It's a little bit smoother into the torque profile. but the overall energy generated by the hip is also significant, right? So I think one challenge is think of the joints from the biomechanics perspective. For example, many people think about the knee joint is not a very not super useful, but if you think about stair climbing or people with disability, the knee joint tends to be a very important joint, because for level ground walking, knee joint is like a damper. It doesn't really generate much positive energy. So that's people don't really kind of consider this joint as much as the ankle joint. So overall, I think ankle joint has been kind of like well studied. Then the hip joint, the third joint, the third is a knee joint. Maybe you can think about a little bit of different application, different based on the different joints. I think that's something can be considered for the competition. And also, some tentative idea is for soft robots in general. For example, it's kind of like a unidirectional. For example, many soft robots can only assist the flexion or extension, single unidirectional assistance. Can you think about something that can really assist both flexion and extension, right? I think that's a grand challenge for soft robot with application in for locomotion or for even for manipulation. Yeah.
Great answer. Thank you. Any other questions from the students? Don't be shy, please. There's no wrong questions. I think all our speakers are willing to get questions. If you send them to them directly via their email, would be willing to respond and provide you any feedback or suggestions. Actually, I have one more question, Dr. Su. So a lot of your work has been in the lower limb. Can you talk about how does this work apply to the upper extremity, and whether some of your techniques would readily apply to supporting soft robotics and exoskeletals for upper extremity activities?
Yeah, that's a good observation. Yes, right now we primarily focus on the lower limb application, but the technology, the actuator, can also be used for upper limb. And for upper limb, it generally requires less torque, right? So, but the challenge is typically has a more degree freedom, no matter for the hand or from the other upper limb, from the hand, elbow, wrist, and shoulder. So actually, in my lab, we also have a project sponsored by the National Science Foundation to develop soft upper limb exoskeletons to help workers and also people with disabilities. So it's kind of like the same technology, but it can be used for different applications, but it requires some kind of customization. Yeah, Stefano, do you want to?
Yeah, thank you. Thank you so much for your amazing lecture. I would like to discuss with you this issue. I think it's growing in our community. That is the importance of, let's say, promoting the diffusion of robotics for rehabilitation and assistance. As you have already anticipated in your talk, we have already experienced the first phase, let's say, of pioneering exoskeletons coming from other, let's say, concepts such as the augmentation of soldiers. So the exoskeleton coming from these experiences are a kind of spin-off. Now, based on your experience and the introduction of soft technologies will help to decrease the cost, or are we going to experience again a rise up of the cost and the prices for the final products? Because we are aiming also to diffuse these technologies in the hospital, rehabilitation center, and when possible, private purchase. So my question is, what about affordability of robotics in this new revolution, in this breakthrough provided by soft technologies? Thank you so much.
Yeah, that's a really, really good question. I think currently one key barrier for the acceptance of exoskeleton is the cost, right? Generally, for example, for single joint exoskeleton, for example, for the knee joint, it's roughly about at least 60 to 70K US dollar, right? So it's pretty expensive. I think Soft Robot offers some solution to reduce the cost, because I think, for example, when I talk about this kind of like a soft, kind of like a pneumatic-based solution, I think this is really, really cool, because not only because it's soft, also because it can potentially reduce the overall system cost. Because you see, we don't need those kind of like a lot of like a high precision machinery, like a gear, motor for the like the traditional rigid robot. I think that is from component technology, it can significantly reduce the cost, right? But I think we certainly need to have better understanding, right? How significantly can we reduce the cost, right? And better quantify this cost reduction. And certainly you can see here, there's some components, for example, the motors, the pump, in our case, it's still not very cheap, right? And even it's softer. I think we also need to think about some kind of like a motor pump to further reduce the cost. I think overall, Soft Robot can reduce the cost, but it can be through some like a motor, just a little, because it still has a little bit of rigid component, right? Can we further reduce cost? The good news is kind of like in the rigid robot, like the quasi direct drive, people are using the Jones motor. Those motors are kind of cheap. It's about actually about $100 if you only think of the motor itself, right? That's why in my lab, we are also working on the electronics, the motor driver. So we can further reduce the cost from the motor, electronics. So overall, it's kind of like several key components, like let's say motor, pump, and electronics, right? So if we can further make those simple and affordable, we can certainly significantly reduce the cost of soft robots, which is already cheaper, more affordable than rigid robots, right? I think that's certainly a very, very important aspect. And also, for assistive robots, in general, we don't need a very precise control, right? We don't need to precisely track the torque. So that's something we can sacrifice through a soft robot solution, right? It's like a human, right? We're not super precise. It's kind of like roughly correct, right? So I think this is a unique application and a unique opportunity to reduce the cost.
Thank you so much.
I think that's good.
Thank you so much. So I think these are great news, and so great expectations are on the way for the final user and also for us as a community. Okay.
Yeah,
Okay.
You have been doing a lot of great work, so maybe we can explore this direction together with Dr.
So thank
Johnson.
you, Dr. Su. Our next speaker actually is teeing up right now. Thank you for such a wonderful workshop and presentation. I would actually even suggest that, you know, to the attendees that Dr. Su had given a link, you could put it in the chat, to a lot of his publications. He listed a lot in his talk. His publications probably are good ones to reference. So I would say if Dr. Su could put his contacts so you could get to his publication list, that would be awesome. And we're going to transition to the next speaker right now. Again,